I had a look at the result of the previous session, and the writing was very clear. I'm hoping that once YouTube process it, because I don't know what YouTube actually does to the videos that are uploaded to it. I assume, you know, they're YouTube, they're the biggest video repository in the world. So they, as far as I know, they're probably doing all kinds of processing to the videos they receive. So, but initially the writing was clear. I could read it easily. So let's hope that once YouTube finish with it, that will remain to be the case. Right. Well, in this session we just continue on with it's pretty like a second case of solving the STIE, which is now short for the Schrödinger time-independent equation, the STIE, S-T-I-E, the STIE. Okay, so we'll now do our second example of a STIE, solving it. It's a bit more complicated because this time it's not in one dimension, it's in three. Right? So instead of having a region on the x-axis and the potential V is 0 inside that region, but infinite outside that region. Now we have something similar, but in three dimensions, and not just a one-dimensional region, but a box, three-dimensional box. So we'll have an x-axis and a y-axis and a z-axis, and the dimensions of the box in the x direction will be a1, a1 minus a1, and in direction y, the y-axis, it'll be a2 and minus a2, and in the z direction it'll be a3 and minus a3. Okay, so it's in conception it's pretty similar to the previous session's case, but now in three dimensions. Okay, so outside these three areas, so here the potential's nothing inside the box, right? This three-dimensional box, and the potential's infinite elsewhere. Right? So so inside the box, in that region, your STIE, your Schrödinger time-independent equation, will have this form now. Now in three dimensions, right? So the complexity goes up a little bit, but it's pretty similar to what you're used to from the one-dimensional STIE, right? Except now you've got partial, twice, what's the word? Double, partial, twice. I don't know how to say that. Second order, I guess. Second order partial differential in y, and second order partial differentials in z, right? So you've got this form, and u now, your wave function is no longer a simple function of x alone. It's now a function of three spatial parameters, x, y, and z. Okay, but it looks familiar. It's sort of what you used to, except for these two extra terms, and u is now a function of three variables instead of one, right? Now, if you're used to solving partial differential equations in three dimensions, if you see something like this, the general form of the solution to your u is of this form. And you've seen that sort of thing before in the one-dimensional case, right? But now we're in three. And your e, if you take this and you differentiate it twice by x and add to it by y and z and so forth, you'll get this kind of thing. Now you've seen something like that before, but we only had one term, like the alpha 2 and alpha 3, they weren't there. We just had alpha squared, h bar squared over 2n. Okay. Now the usual procedure. Now we're starting to get into a bit of a habit now. We picked up that habit with the first time. Okay, we've got the form, the basic form of a solution to the wave, for the wave function. Now we start imposing constraints on it. Continuity, what's the word? Normalization, and the gradient had to be, the two gradients when they meet have to be same, no discontinuity, that kind of stuff. All right, those three conditions. All right. Now, at the boundaries, when x is plus or minus a1, or y is plus or minus a2, or z is plus or minus a3, at those boundaries, your u has to be 0, because outside those regions it's 0. So at the boundary, for reasons of continuity, you have to have these constraints met. And when you impose those constraints, similar. Now I'm glossing over the details, but you can calculate this stuff for yourself as homework, because it's just a fairly straightforward extension of the techniques that we used in the previous session for the one-dimensional problem, right? So imposing these continuity constraints, you get similar solutions to your alphas. And instead of having just one alpha now, we've got 3 of them. One for each dimension, x, y, and z. Okay, and you'll have now 3 integers, n1, n2, n3. And you get this condition for alpha 1 is that it's equal to some integer n1 times pi over 2a1. Right? And similarly n2 times pi over 2a2, and so on, for the 3 cases. And hence the energy E will be now we know these alphas now, right? We've got values for them, these 3 values. So we plug them into the formula here involving alphas, and you get this kind of thing. So here's the energy now. Now again, it's discretized, right? It's discrete. It's not continuous. This energy E will depend on the values of 3 different integers, n1, n2, and n3. They're all integers, right? This energy here is not continuous. It doesn't change. It cannot take on continuously changing variables. The values that E can take are of this form, right? And with discrete values. Now, on this path, we pick up a concept that we'll use later that's useful, but because it's relevant to what's going on right now, I'll mention it. And the technical term for this new concept is called degeneracy, degenerate. In ordinary English, you'd use the word degenerate as an adjective if somebody's living a really degenerate lifestyle, meaning totally undisciplined, dirty, poor health, doesn't exercise, smokes, drinks heavily, beats his wife or husband, or, that lifestyle is called degenerate. To degenerate means, in a sense, to go down, right? Now, in this technical context, degeneracy has quite a different meaning, although I suppose related in some sense. Degeneracy occurs when you have 2 eigenfunctions or more that have the same eigenvalue. Now, in the case of the STI, the Schrödinger time-independent equation, your eigenvalue, remember, is the energy, right? Yeah, that's your eigenvalue. So, like here's your operator L, your differential operator L. Here's your eigenfunction, that's your eigenvalue, and there's your eigenfunction again, right? So, degeneracy, or a degenerate eigenfunction occurs when you have 2 different eigenfunctions. Like, now here's an eigenfunction, right? There's your eigenvalue. When 2 different eigenfunctions, here's a different eigenfunction from this one. But if those 2 eigenfunctions have the same eigenvalue, like lambda 1, then these two different eigenfunctions are said to be degenerate, right? They have the same eigenvalue. Like you can just see it, like just looking at this. Obviously, this is an eigenfunction, right? Because you get the same here. Similarly, this is an eigenfunction because these 2 are the same. But they both have the same eigenvalue. Therefore, this eigenfunction are degenerate, right? Now, in this special case, we can if we make appropriate adjustments, we can arrive at degeneracy, where the eigen functions, or in this case wave functions, are degenerate, meaning the eigenvalue be the same, and in this case the eigenvalue is the energy. Okay, so here's our formula for. Let me put a bar around that because it's sort of important. That's the formula for the energy in the three-dimensional case of the box. Okay? Now here's a special case. Let the dimensions of the box be, well, let the box be a cube. Okay? So A1 and A2 and A3, they're all the same value, and let it be A. So the cube, the side of the cube, is has dimension A, size A. All right. Well, so these are all the same. So you can take the A and bring it out here. So it'll just be A squared. So you get your A squared now underneath here, right? No longer underneath, but you put it here. All right. Now these are integers, right? Positive integers starting at 1. You know, can't be 0 for. You can't have all these 0 for the reasons we gave in the previous session. Because if they were all 0, then your E would be 0, and therefore your U would be 0, and therefore the particle is not in the box. And it can't be 0 for reasons of the Heisenberg uncertainty principle. So you know, there's the same logic as the previous session. Okay? But we can get the same energy, and hence the same eigenvalue, for different values of n, for these different integers. Now, here, watch. Say I let n1 be 1, and n2 be 2, and n3 be 3. So I get 1 squared plus 2 squared plus 3 squared, that's 14. Okay? So the energy then for 1, 2, 3 would be 14 times h bar squared pi squared, blah, blah, blah. Right? But if I now choose n1 to be 2, and n2 to be 1, and n3 to be 3, so 2, 1, 3, I'll again get 14. And similarly, if I choose 3, 1, 2, I'll get 14. In fact, there are 6 ways you can order those 3 numbers. Right? It just comes out of the combinatorics, you know, permutations and combinations. You probably did that in high school, right? So there's, if I just choose the numbers 1, 2, 3, there's 6 ways I can order those 3 numbers. And you know, here they are. And each of those 6, you know, those 6 orders of integers 1, 2, 3, give me the same energy, right? So I have 6 times the same eigenvalue. In other words, the energy. The energy is the eigenvalue in the STI, Schrödinger time independent equation. All right. So I have here a kind of 6-fold, you know, 6 times, 6-fold degeneracy. Right? So I have 6 eigenfunctions that